Hi, welcome to the Dynamics tutorials. So for this problem we have a slider that's at A. It starts from rest, the motion's in the vertical plane, and the slider is going to slide down to B. At the same time we have a rope that's attached that goes through a pulley, and then there's a force of 20 newtons acting on the rope. And so we're going to use work and energy to solve this problem. Because work and energy is going to allow us to relate velocity to change in position, which is exactly what we have for this problem. So we're going to solve for the velocity right before it strikes the bottom here at B. We can start off by looking at a free body diagram just so we can make sure that we're capturing all of our forces. We have a normal force that acts on it. We have a force here from the tension of 20 newtons that acts on it, and then we have a weight. Looking at this force is constant in magnitude, but the angle is changing. So if we treat it that way, we're going to have to integrate it over this path, because even though the magnitude is constant, it's not a constant force because the angle changes. So an easier way to look at that would just be to see how much the force moves over here, and however much work it does over here was the same amount of work that it would have applied to A. So looking at this, we have our length of the rope when the slider's in position A. That would be our 2 meters squared plus our 1.5 meters squared. Add them together, take a square root, we get the 2.5 meters. And then when the slider's in position B, we only have 1.5 meters of rope. So subtracting that, that tells us that the rope changes 1 meter in position over here. And then we can do our work and energy equation. So our initial kinetic energy plus the work done moving from position 1 to position 2 gives us our final kinetic energy. So our initial kinetic energy is 0 because we're starting from rest. Then we have to include the 20 Newton force. We'll multiply that by the 1 meter change in length that we just calculated. It's positive because it's adding energy into the system and speeding the particle up. And then we have the W times delta Y, the minus W times delta Y term. So that would be our, miswrote on the board there. I have meters and should be kilograms. So that's the 0.5 kilograms of mass that the particle had. Looks like I forgot to jot that down. Let me just write it up here. Times the 9.81 meters per second squared, and then times the 2 meters that it's falling. It's negative here because it's below its starting point, so it's a negative delta Y. And then that's equal to the final kinetic energy, which is the 1/2 of that mass times the velocity at B squared. And then we just rearrange, make sure that you always take the square root when you're solving for velocity with work and energy, because you have velocity squared, and you'll get that the velocity at B is 10.9 meters per second. Thanks for watching.